I'm Wiebke, PhD candidate at Delft University of Technology. I'm presenting my work on bias in automated speaker recognition, which I have done under the supervision of Aaron Deng. Our paper presents an evaluation framework to quantify performance disparities in speaker verification. We use the framework to evaluate bias and show that it exists at every stage of the machine learning development pipeline. Based on our insights, we recommend research directions to address bias in speaker recognition technologies. I will start with our motivation and an overview of speaker recognition. We'll explain our research approach and evaluation framework, and will then present the results of our analytical and empirical study of bias in the VoxLab Speaker Recognition Challenge. Finally, I will conclude with recommendations to mitigating bias in speaker recognition. Speaker recognition consists of three core tasks: identification, which determines who spoke; diarization, which separates speakers; and verification, which tests if a speaker is who they claim to be. The last task can be seen as voice-based biometrics. The tasks are closely related and share many aspects of their development process. Speaker recognition, so what, you may think? Well, at Safaricom in Kenya, my voice is my password. At BBVA Mexico, my voice unlocks continued access to my state pension. At First National Bank in South Africa, I can enable voice biometrics to access mobile banking services. Speaker recognition is pervasive and increasingly used in high-stakes applications, such as mobile banking, proof-of-life verification of pensioners, and call centers offering public and private customer services. It also adds a security layer to billions of voice-enabled mobile phones and smart speakers. In this paper, we study bias in speaker recognition with a focus on speaker verification. In adjacent fields like face recognition, natural language processing, and automated speech recognition, bias is known to exist. This gives us a good reason to expect that speaker verification is also likely to be biased. Here's a quick overview of how speaker verification works. A speaker verification system takes two speech utterances as input. The enrollment utterance belongs to a verified person and is typically stored in the system. The trial utterance belongs to a person that seeks access to a voice-secured service and is compared against the enrollment utterance. Features are extracted from the raw audio files of the utterances and used as input to a speaker embedding model to create embeddings. Today, the models used are typically deep neural networks. The outputting embeddings of the two utterances are then compared with a similarity scoring function, which outputs a score. The system is tuned to a threshold and accepts or rejects speakers depending on whether they lie above or below the threshold. Given this system, speaker verification is evaluated based on the false positive and false negative error rates. A false negative error occurs when utterances of the same speaker are rejected, while false positive errors result in different speaker utterances being accepted. So simply put, if I try to access my system and I get rejected, then that is a false negative error. If somebody else tries to access my system and they get accepted, that is a false positive error. Detection error trade-off curves can be plotted during evaluation to visualize the trade-off between the false positive, which is on the x-axis, and the false negative, which is on the y-axis, the error rates of the two. So while the DET or detection error curves show the potential performance, the system is ultimately calibrated to a threshold that is determined by minimizing a cost function that weights false positive and false negative error rates. To analyze bias in speaker verification, we draw on Suresh and Gutak's framework for understanding sources of harm in the machine learning lifecycle. They categorize harms arising from 7 types of bias during data generation and model building and implementation. Next, I will discuss our research approach and then the results of our study. We conducted an empirical and analytical study of group bias in the VoxLab Speaker Recognition Challenge. The VoxLab SRC and its associated datasets are a popular technical competition, and using it as a case study allowed us to systematically analyze bias throughout a prototypical speaker verification development workflow. We evaluated two models with different sizes. The one has 8 million, the other 1.4 million parameters. This difference is mostly due to their different input dimensions. Other differences include frame level aggregation, the loss function, and data augmentation strategies. We evaluate the models on the VoxLab1 dataset and establish subgroups from speakers, gender, and nationality as categorized in the dataset's metadata. Finally, we evaluate disparate performance at the threshold to which the system is tuned by calculating subgroup bias as the ratio of a subgroup's cost to the overall cost at the threshold. We designed an empirical bias evaluation framework for speaker verification that takes pairs of single speaker speech utterances from the VoxLab1 evaluation datasets as input. The utterances are passed for scoring to the two pre-trained baseline models that I described. And then using labels from the VoxLab1 metadata, we assess performance across all gender and nationality groups. Finally, we quantify bias on disparate predictive performance across groups at the threshold to which the system is tuned using subgroup bias ratio. Now, let's dive into the types of bias that we found. I will start with historical bias. The automated data generation pipeline of the VoxLab1 dataset starts with candidate speakers from the VGG face dataset. This dataset is created from the most searched names in the Freebase Knowledge Graph and IMDb movie databases. It then uses a hog-based face detector to track faces, SyncNet to identify active speakers, and VGG Face CNN to verify speakers' identity. In this way, the pipeline reinforces popularity bias in search result and directly transfers bias in face recognition to speaker verification. Given this historical bias, there is no surprise that we find representation bias in the dataset. The dataset is skewed towards males and US nationals. As a celebrity dataset, it is also not representative of the broad public. It is likely that VoxLab1 contains representation bias that affect many other sensitive speaker attributes than the ones we have evaluated. For a benchmark dataset like VoxLab, representation bias is particularly problematic, as it shapes the research culture of the domain and influences future research directions. Now, measurement bias typically occurs in the process of designing features and labels to use in the prediction problem. In speaker verification, target labels are exactly known and undisputed, which means that this kind of measurement bias does not arise. However, the binary gender and nationality labeling choices in the metadata influence how we consider representation in the dataset and how we design subgroups for evaluating bias. They thus introduce their own form of measurement bias. When disaggregating performance curves for male and female speakers of different nationalities, we can observe aggregation bias. Here in the slide, the dotted black DET curve, very faint, shows the overall performance across all subgroups. DET curves performing worse than average, DET curves above the dotted line have a high likelihood of performing worse than average, while DET curves below the dotted line will generally perform better than average. It is easy to see that the DET curves of female speakers on the left lie mostly above the average DET curve, while those of male speakers lie below it on the right, in the plot on the right. The model is thus likely to perform worse than average for females and better for males. The triangular markers show the false positive rate and false negative rate at the threshold where the overall system cost is minimized. The markers for male and female speaker subgroups are dispersed, which indicates that systems operating performance vary significantly across subgroups when calibrated for aggregate performance. Model performance varies across the two models that we evaluated. This is to be expected. However, we found performance disparities across subgroups amplified by the smaller model architecture, indicating that modeling choices such as input feature dimensions and the choice of optimizer can propagate learning bias. We can see here that learning bias exists not only at the threshold to which the system is tuned, but across the entire DET curve. Here it is clear that the larger model in green performs better than the smaller model in purple. What is interesting, though, is that this is that the distance between the DET curves for males and females is greater for the smaller model than the larger model. Moving from DET curves to subgroup bias, where we see this to subgroup bias, here we see the subgroup bias for each subgroup for the two different architectures. The key takeaways are that both models tend to perform better for male speakers than females for almost all subgroups. The male speaker subgroups, which are the crosses, are in the bottom left corner of the graph. What's interesting is that while the larger model on the x-axis performs better for some subgroups, the smaller model performs better for others. This leads us to believe that significant work remains to understand how learning and engineering choices affect performance disparities across speaker groups. Evaluation bias is attributed to a benchmark population that is not representative of the user population and to evaluation metrics that provide an oversimplified view of model performance. We observed evaluation bias due to datasets and metrics. This is an overview of the speaker representation in the 3 evaluation sets of Voxelab 1. Voxelab 1 test consists of 40 speakers whose name starts with an E. Voxelab 1E consists of all speakers and utterance pairs that have been randomly sampled across speakers. Voxelab 1H is considered the hard evaluation set and only includes different speaker pairs that have the same gender and nationality, provided that there are at least 5 such speakers in the subgroup. So we can look at representation on 2 levels. We can look at it on the speaker level, which is more common, or on the utterance level, which is not done. What is interesting to note is the representation on an utterance level quantifies the amount of data available per group. So not just who's included, but how much data for everybody that's been included. And so we see here that for all evaluation sets, the utterance level gender representation is worse than the speaker level representation, with female representation dropping 2.5 to 8.5 percentage points. Given that these evaluation sets are quite different, we can also see that model performance varies quite dramatically across them. So on Voxelab 1 test, the small data set, and Voxelab 1E, the random data set, we can see that the performance is similar, even though the pink line representing the small data set is rugged, showing that the evaluation is not robust. If we take the same subgroup data set, here the blue line, we see that performance is considerably worse. I will skim over the shortcomings of current evaluation metrics. The equal error rate, which is frequently used, cannot weight false positive and false negatives differently. It's also an oversimplified view on performance. The minimum detection cost has its own challenges. And ultimately, both the equal error rate and the minimum detection cost optimize average performance. Moving on to deployment bias, which arises when application context and usage environment do not match the problem space as it was conceptualized during model development. We consider deployment bias arising from application context and due to post-processing. So we see a change in application context where the use of speaker verification is expanding beyond intelligence and security applications to voice assistants, small devices, and also call centers. We are also seeing that the trade-off between false positives, which is good for security and privacy, and false negatives, which affects usability and access, is not considered during evaluation and not considered in light of the changing deployment application contexts. And finally, coming back to utterance pairs in evaluation datasets, they currently do not reflect emerging deployment contexts. In a smart home application, for example, a realistic difficult utterance pair should compare my voice and my sister's voice or my mother's voice, rather than my voice and some random male speaker's voice with like speaking another language with a different accent. One source of deployment bias due to post-processing is the choice of threshold to which the system is calibrated. The triangle markers show performance at the overall threshold, while the crosses show performance if subgroups were calibrated to their own minimum. Here, for all subgroups, the threshold at the subgroup minimum shifts the false positive rate and false negative rate closer to those of the minimum overall threshold, suggesting that performance will improve when optimizing thresholds for subgroups individually. And now finally to our recommendations. We recommend strategies for building inclusive evaluation datasets that consider real usage scenarios and evaluation metrics that consider the consequences of errors. We also highlight learning and engineering interventions that present promising approaches to mitigating bias. Our recommendations are by no means conclusive, but offer a first step in this direction. Inclusive evaluation datasets should contain utterance pairs that reflect the application context, sufficiently represent speaker groups on a speaker and utterance level, and consider speaker diversity across languages and accents and across vocal characteristics. Guidelines are then needed for application-specific error metrics, acceptable false positive and false negative error rate ranges, for weighting error rates in the cost function, and using alternative metrics. We also recommend that disaggregated evaluation across speaker groups becomes standard practice. Some of the learning and engineering interventions that we believe have high potential for reducing bias are calibrating subgroups to their own threshold and dynamically adjusting thresholds to individual speakers if possible. In addition, we see more research needed to understand the impact of measurement bias and how it arises during data processing and feature extraction, as well as algorithmic bias and how it varies in cloud and on-device settings. This brings me to the end of my presentation. I invite you to read our paper for further details.